let's go ahead and practice actually drawing some Lewis structures and predicting electron geometries based on the Lewis structures that we draw. This first one up here, I have the acetaldehyde. This is the formula for it anyway. So if you're going to draw this Lewis structure, and Lewis structures of molecules with a little bit more complicated formulas than, like, say, NH4, you will need to know that there are some conventions about the way the formula is written that actually give you some hints as to the way the molecules are arranged. So if you see carbons in a row like this, those carbons are essentially bonded to each other. The hydrogen are bonded to the carbon to the left of them, okay? And carbon will always have four bonds to it, okay? So it's always got to have four bonds. So let's go ahead and try drawing this structure here. Well, first off, let's find the total number of valence electrons, which is always a good first step. So if we look at carbon, is in 4A rows, so it's got 4 valence electrons. So 4 valence electrons, but there are 2 in this formula, so it's 4 times 2. Hydrogen has 1 valence electron. But there are 4 of them, so we do times 4. And then finally, oxygen has 6 valence electrons, but there's only 1 of them, so that ends up being 8 here, 4 there, and then 6 there. So that's 12 plus another 6 is 18, I think, if I did my math correctly. So now let's actually draw those element symbols in a good spots appropriate for the formula. So we have carbon. It looks like there are 3 hydrogens bonded to this carbon. Hydrogen, hydrogen, hydrogen. Then we have another carbon bonded to it, shown here, carbon bonded to this carbon. And remember, carbon always has to have 4 bonds. Now if we bond this carbon, or bond it to an oxygen here, and then we have a decision. Do we put the oxygen on the last hydrogen on the oxygen, so like this, or do we put it on the carbon? Well, if we put it on the oxygen, like so, that means that carbon will have to have 2 lone pairs of electrons, or it's got to have, instead of one of those lone pairs, it has to have a double bond to that oxygen. Now, if that's the case, oxygen will all of a sudden have 3 pairs of bonding electrons, so pair here, pair here, pair there, have 1 and 1 pair of non-bonding electrons. The structure for this is not so good because carbon, the reason why this is not the best structure is because carbon will always have 4 bonds. So all of its electrons will always be involved in bonding, and so this hydrogen will, in order for that to occur, this hydrogen will have to actually move over here. So this is the actual structure we're going to use. H, 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 carbon with a hydrogen here, and then an oxygen there. Now we fill out our valence electrons. Well, if you notice right here, carbon's only bonded once, so we know that we need to put a double bond right there for carbon to have 4 bonds, or excuse me, yeah, 4 bonds to that carbon atom. If we do that, fill out those valence electrons, we put it there. If we look at this structure, do we have the right number of electrons? We have 2, 4, 6, 8, 10, 12, 14, 16, 18. That's the correct number of electrons. We have our Lewis structure here. Now let's consider the electron geometries around the central atoms. We have this central atom and this central atom, okay, so 2 carbons. For this atom, we have for this atom, this carbon, we have 1, 2, 3, 4 electron domains, 4 E- domains. The name of that particular geometry, a geometry with 4 electron domains, is called tetrahedral. Tetrahedral. Go back to those tables if you didn't remember that. So eventually you're going to have to memorize those tables, but at this point I'm just going to give it away. This one has this carbon has 1, 2, 3 electron domains. Remember, this counts as a single electron domain, so that's 3 electron domains around this carbon. That one is called trigonal planar. Running out of room, planar. So trigonal planar. There's supposed to be an L right there, but it keeps deleting it on me. Okay, so that would be the shapes of the electron domains around those central atoms. So check out this molecule here, or this ion actually. Remember, for ions, in order to actually show that it's an ion, we're going to have to draw the Lewis structure inside big old brackets like this and put up the charge on the upper right-hand side of the bracket. Figure out the valence electrons. Nitrogen is in a 5A group, so it's got 5 valence electrons. So N is contributing 5 valence electrons. There's one of them. Again, hydrogen contributes 1 valence electron, but there are 4 of them. So that's 4 and 5. So we should have 9 valence electrons. Since we have a plus charge, what do? Hold on, pause the video, make sure you know what to do. Okay, now that you're back, that means we subtract one of these valence electrons off, so this should have a total of 8 valence electrons. Well, we'll obviously put nitrogen in the center. It's bonded to 4 hydrogens, right, like that. 4 hydrogens is our Lewis structure. Does this have an octet? And do we have the right number of electrons? We have 8 electrons, and nitrogen does have an octet of electrons, so that's our Lewis structure. Well, what's the geometry, electron geometry around this molecule? If you look, 4 electron domains here, 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 and here. So the electron geometry is tetrahedral. Tetrahedral. Last. All right, let's do one more molecule that has a little even longer formula here. This one is actually called glycine. Which is not, you don't have the nomenclature rules to actually name that, and glycine is a common name anyway. So let's go ahead and actually look at the number of valence electrons. So nitrogen, oh, wait a second. All right. So nitrogen has 5 valence electrons. There's one of those in the formula. Oxygen has 6 valence electrons. There's 2 of those in the formula. Carbon has 4 valence electrons, and there are 2 of those in the formula. And then hydrogen has 1 valence electron, and there are 5 of those in the formula. 2, 4, 5. Yep, 5. So we have 5 and 8 and 12 and 5. So 12 times 8 is 20 plus 5, 25, 30. 30 valence electrons total. So let's go ahead and figure out where these elements need to go in relationship to each other. So we have nitrogen, which is bonded to 2 hydrogens. So we got nitrogen, hydrogen, hydrogen. That nitrogen is also bonded to 1 carbon, which has 2 hydrogens on it. Hydrogen, hydrogen. Now that carbon is bonded to another carbon that may or may not have a hydrogen on it. Let's figure this out. So we have it bonded to 1 oxygen here. We have it bonded to another oxygen there. And in order to get a third bond, we could put a hydrogen here, or we could put a hydrogen there and put a double bond there. Now this is actually the correct shape. If you put a hydrogen here, however, you would have an okay shape, but then you would have one of your oxygens having a negative charge on it, because if it was here, you would have, both of your oxygens would have a negative charge. You need to have 2 things bonded to oxygen in order to have a minimal formal charge on that oxygen. Let's go ahead and fill up our octets. We go 1, 2, 3, 4. Now for this oxygen, we have 1, 2, 3, 4. All right, we have an octet for the carbons, all of the carbons. Nitrogen, we still need 2 more electrons because it's got 2, 4, 6. Need 2 more electrons. This right here should have 30 electrons shown. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So this is our Lewis structure. Now talking about the geometries around here, this has got 4 electron domains around it, so it's tetrahedral around the nitrogen, tetrahedral. Here, it's also tetrahedral here, What about there? How many electron domains do we have? We have we have 1, 2, 3. Remember, this only counts as one electron domain. So right there is not octahedral, trigonal planar. Trigonal planar. It's got two electron domains. Around here we have 4 electron domains, right? 1, 2, 3, 4. And so that's also got a tetrahedral. Hedral electron geometry. And so those are the electron geometries for all of the atoms, so what we consider central atoms for that particular molecule.